We don't know why we...
Hey everybody, welcome back to HPC Tech Shorts, the engineering water cooler here in AWS. With me today is Evan Statton, who's a principal solution architect in our media and entertainment group, and he's based out of Colorado. Hey, Evan.
Hey, thanks for having me today. Can I first compliment the fact that this show has an intro with music and graphics? Like, that's awesome.
We're high tech here, and it cost me all of like $75 on Fiverr to get that done.
Well, but seriously, like a little production value goes a long way sometimes. Like we're here to talk about we're here to talk about media today. So like, look, both of us have these microphones. We got an intro thing.
The thing that we're talking about today, this is a little bit of an unusual topic for an HPC channel, because what you guys have done is you've taken one of the technologies that we built for like sending millions of packets a second all over the network to keep really tightly coupled scientific applications coordinated in a massively parallel thing. You guys have taken that and you've ported it over into a broadcast digital video space where, in ancient times I had a little experience and a bit of exposure, and you've used it for something we totally did not expect. And that is cool. And that all on its own, that is a reason to get here today. But there's also one other thing that we have to mention in this bit is one of the things that came out of that collaboration we did with you guys is you forced us, the HPC engineering group, to figure out how to deploy EFA on instances that were smaller than the whole box. So in particular, half-size instances. And so today, when people are watching this, you'll be able to go to your EC2 console, you'll be able to launch instances like, say, a C5N 9x large and get EFA with it, rather than always being forced to go for the largest size. And that's because the largest size we designed it for, it was always designed around HPC workloads, but we now have a new member of the HPC family, and it's CDI. So
great. I'm excited about the tech. I'm excited to see a collaboration between the HPC and the live video worlds. It's exciting to be here, not just on your show, but like in this moment in the industry where these things are happening. It's really interesting and exciting.
It is definitely a weird thing to be doing. So,
yeah, well, let me, I guess, start by saying why half-size instances are interesting for video customers. Whereas like in HPC applications, you need a lot of network and you need a lot of compute because you're doing a lot of work. Video has this, it's a little different than what the gigantic, like .metal instances are. They need a lot of network because uncompressed video is big. So you need a large amount of network bandwidth between instances. But then like, if you look at the G4DN .metal, there's like 8 GPUs on there. And so a lot of video workflows, they don't need 8 GPUs. They need, one or 2 GPUs. Right. Yeah. So customers, rightly expressed frustration with that and, essentially asked us to come out with instances that were right-sized for their workflows. So that's where this idea of the half-size instances came from, so that customers could use something like the G4 8XL, which has 50 gigabits networking throughput and also 1 GPU, and costs about a quarter of the amount of the .metal.
And the reason why the collaboration came about is, in digital video land, it's video goes through so many different steps in a production process before it actually hits the TV screen in your house. And it's the transfer point between any of those processes. Usually, like back in the day, we used chunky coaxial cables to move the video, shoot and capture between all these machines.
Right.
Fast forward to the 21st century, and we get to the place where it moves around on networks. But what we can't do is have networks introducing a latency factor, like milliseconds worth of transit time, because then it starts to show up really like big time. You see those differences in a production studio, right?
If you have somebody who's doing camera switching and, they have to switch from one camera to the next and the director's calling for that, you need to be able to hit a button and have that provide you feedback right away. You don't want to be
Mm.
waiting seconds or even milliseconds really for that.
And it's that milliseconds bit we should talk about, because in your space, with video flicking by at 60 frames a second, one frame is 16 milliseconds, right? And we designed EFA to be, responsive down at the, in the order of microseconds kind of territory. So we've definitely got the right technology for, we're in the right latency ballpark. And then the next level of latency really comes from how long does it take for you to shove quite a lot of data from one place to the next and make sure you recover when packets get lost and all that other stuff. And of course, EFA has been designed for getting maximum throughput in quite hostile environments, where you just have to take into account that packets are going to get dropped and they're going to go missing. And
can I say why it's a lot of bits flying around? Because a lot of people are like, what are you talking about? I can stream this on my, iPhone or whatever. And that at that point, it's not a lot of bits, but that's after it's been compressed. So for those who are working on active pixel data and actually need to manipulate the content of the screen, you're working in the uncompressed domain, which means you're describing every pixel individually because you need to be able to do math on them, essentially, if you need to add graphics or do fades or switches and stuff like this. So at that rate, like if you're thinking about 4K, 4K is like 21p, 60 frames a second, and you're describing every pixel for every single frame, and you need to do that for some part of the production chain, you're up at like the 12 gigabits per second mark, and there's no time for retransmissions really, because if you start inserting like TCP type retransmissions, then you end up in a situation where some of the frames might be late, and that's not really acceptable either.
Then you're in that place where some person working in a control room touches a button on a surface of a deck and they don't get that instant response. They start to see a laggy response. That messes with operators' heads, right?
Right. And the other thing is that the timing has to be uniform across all of your sources. So for example, if you have like 10 cameras in a baseball stadium or, some sporting event, all those cameras are timed to be taking their pictures at the same moments, so that if you switch between one camera to the next, you're seeing the same moment in time represented by different angles, essentially. And so if you have this non-deterministic lag that could happen, then all of your sources will be out of sync and the production won't work. So you need very high reliability of latency and throughput and timing.
Let's put some images to this so that people understand what we're really talking about here.
So there's really only five or six things that are happening in this diagram, and what we're seeing is a dual pipeline experience. So you basically have redundancy built into this diagram. So what's at the top and what's at the bottom in the two availability zones are the same thing repeated intentionally. So let's start by saying you're right when you're talking about the bulky coaxial cables on-prem. And so when the broadcast industry began its migration to IP, and we realized that we needed to move uncompressed video around in that on those wires, the first thing that we did was we invented something called, well, not the first, but eventually we got to a standard called 2110, which describes packets that go over single Ethernet wires for the most part. So it works similarly to the SDI domain, where you're sending packets through one gigantic UDP stream. And that works really well on on-prem networks because you can design the network, you're designing it for a certain use case, and you can make very few paths, and you could say, I'm going to optimize this for gigantic UDP flows. And so the need for CDI came, and thus EFA and SRD, because the cloud network is just different than that. And so in order to get uncompressed video to work in the cloud environment, which the network is giant and it's a more generic network that's supposed to support many workflows, we needed to have a way that used diverse paths through our network, which is what the SRD protocol does, and also help with some of the kernel bypass needs. So packetizing 12 gigabits per second in CPU and sending it out detracts from your application's core, which in this case might be playout or encoding or something like that. Those are the reasons why EFA and CDI were attractive, because it allows you to move your frame buffer, essentially take your frame data from your memory and just plop it onto the EFA and say, EFA, send it over to the next thing. And it's guaranteed, right? Like that type of traffic is it's a guaranteed delivery. And so one of the metrics in CDI is, was it on time or not? That seemed to be the most important thing. Like I have, remember we said before, 16 and a half milliseconds or so to get my frame from me to you, or from one instance to the next. Tell me if it's late. And that was really our metric for, are we succeeding or not with this technology? Because we want it to never be late, ever. It's also self-healing, right? Like if there's back pressure on one of the, what we call flowlets, or one of the paths through the network becomes not viable for whatever reason, then the underlying protocol will heal itself. It'll tear that one down and build a new one. And the customers don't have to worry about it. That's really the important part. The customers don't have to worry about this. Even when you're developing with CDI, you're not doing any SRD implementation at all, because that's all part of the SDK. And so, the command is really just, hey, EFA, send my frame from here to there. And all this stuff kind of happens abstracted away from the applications, which is nice.
So if you happen to be a chief engineer from a TV network sitting at home watching this, how do you get CDI? Where does it fit in the software stack, and how do I get it and all that stuff?
Well, if you're an end customer, like a broadcaster, you're probably not hands-on with CDI in much the same way that you weren't hands-on with HDSDI or 2110, because you'll go out to a vendor and you'll buy something. And some of the vendors are the same as the ones that they've known and loved for 20 years on-prem. And some of them are new, because software opens up the world to anybody being able to develop these things. We decided to make CDI open source and free, so it's on GitHub and anybody can play with it.
The actual project's homepage is on our main website. That's here, and everything is linked to from there, so you'll be able to find all of this stuff. All right, that's that, like I say, trip down memory lane. We did good. I think that's all there is to say today. For anybody else at home who's watching, if there's anything that you want to see us cover in a future tech short, if you want to see us deep dive on a topic, go somewhere that you're interested in hearing more about, drop us a DM. Our DMs are open on Twitter. Evan, thank you. That was really cool.
Thanks, Brandon.
All right. We'll see you guys next time. Thanks all.